MATLAB Online here. I downloaded the Dynair add-on for MATLAB Online. It was here, and then I uploaded it to MATLAB Online. And I double-clicked on it to install it. Right, so Dynair is ready to run on MATLAB Online. I have unpacked and uploaded the zip with all of these different Dynair files, so I put up on the e-learning platform for you. And let's take a look at one of these Dynair files, the mod file. So, let's see if I can. So in terms of syntax, we see this star thing is one way to write a comment. You can also use the percent sign. It's always a good idea if you write a program to document it, to put codes on it. And even as you're changing things and you want to do something really quickly, the problem is, and so it happens to me too, I have codes where in the moment I knew what I was doing, and then 3 days later, when I want to come back, there aren't comments. I was like, what was I doing here? I have no idea what this code was supposed to be doing. And that's unfortunate, right? So, all right, so this file implements the baseline New Keynesian model, right, from the textbook, in the second edition, chapter 3. And we have Dynair, we've got it. All the variables are expressed in deviations from steady state. Okay, and here apparently they're claiming that the dynamic response to a technology shock is wrong. And we'll take a look at that. Yeah, this was written by Johannes Pfeiffer, who's a friend of mine. He's at the university in Munich, the Bundeswehr-Universität. That's the Army University. But he is, Dynair is a wonderful community. Right, where they have a forum that you can ask questions and try to get them answered. And you'll notice this person here, you see, like, it's his picture. He responds to almost every single question. And that's my good friend Johannes Pfeiffer. It's a nice thing like conferences, when he's has a down minute, he opens up his computer and he starts going through the forum and answering people's questions. So you have, I mean, it's an amazing service that he does to the community. Right, so he does. So the forum, you don't have to always bother him. You can also search the forum. I don't know. You can ask anything about Vietnam. So we have. Right, so there's some questions here about modeling policies in Vietnam without the data. Right, so Johannes Pfeiffer adds in. Maybe look at the exchange rate too. Do this and that. Okay, so there are tons of topics, tons of extra resources here. So we're going to put some stuff together, and there's a user manual. But they have like this online version that you can go through, explaining everything, or you can download it as a PDF. So if you want some late night reading, we have 200 pages, right, explaining all the different things that you can do, or all the different parameters and changes and stuff, and all of it does. Yeah, so it's an amazing resource that's provided free of charge, and a lot of the funding for it. To set them up and Banque de France contribute a lot to it. So it's European open source. We have lots of people at central banks, regional central bank, and anyway. So there we go. Dynair, it's an amazing resource. Glad that Binda has also introduced you to that. So let's take a little bit closer look. So this is written by Johannes Pfeiffer, the online Dynair forum face of Dynair. Right? So if you ever wondered what Johannes Pfeiffer looks like, that's what he looks like. Hi, Johannes. All right, and thanks for giving us this code. So Dynair also has some syntax that allows you to like make changes or do loops and the like. So we don't need to focus on that so much here, but apparently we can set to have a money growth rate rule or not. We're going to see in a minute here. We can also look at an alternative definition of monetary policy from chapter 3. Instead of the Taylor rule, we could do a money growth rule. But we're going to stick with what we had from just now in the lecture. So that's no money growth rate rule, but instead an interest rate rule. All right, and then the way Dynair works, the first thing we have to do is declare what our variables are. And we end the list with a semicolon. You could just put these little names here. The reason why that's important for the program is that the computer sees, it's going to write MATLAB programs for us, is the way Dynair works. And when it's writing a Dynair program for us, if it sees a number, it's going to give Dynair a number. And if it sees a letter, or a sequence of letters, a string of letters, Dynair needs to know, wait a second, are they going to use this as a parameter that they're going to assign a number to? Or is this a variable that they want to determine like an impulse response to? The computer doesn't know, like we know intuitively, we know that when we see y, this is going to be a variable, but Dynair doesn't know, maybe y is a parameter. An even better example, pi, your computer thinks is a number. 3.1415, right? It's the ratio of the circumference of a circle to its diameter. For us, it's inflation. So the computer, if we don't have any way to force the computer to think differently, the computer's going to think that pi is a number, whereas we want it to be a variable. So we first define our variables. All of these sequence, it tells Dynair whenever you see y hat, whenever you see I, whenever you see m, whenever you see any of these letters in this sequence, that is referring to a variable that's going to change over time. Okay, we end our list with a semicolon. And then we're going to tell Dynair there's also a list of variables that are special, that are shock realizations, var exogenous. So we have our monetary policy shock process that we have with a new, did he use new or did he call it? Yeah, new. Right, but this is a process, it's going to be a variable. We only call as exogenous, this var exo, the shock realizations. So this is this epsilon. He calls here epsilon mu. And it's the monetary policy shock, not the process. And now we're going to tell Dynair there's also sequences of letters that are going to be parameters that we're going to assign a number to. And we end that list with a semicolon. And you can do neat things with Dynair. You can add on afterwards, inside dollar signs, the LaTeX code for how you want to represent this. This might be useful in producing figures or the like. It will give you already the LaTeX code. And you can also give it a long name, which can be useful in some contexts. Right, when we see y gap, we know that that means the output gap. Y means output, right? But if you produce a figure that you're submitting or you want to show to, right, it's useful to actually spell out what the names are. So here we have defined the long name of these variables, these are just processes, and also good, what's the name of this parameter? Does it have a name, a meaning? Is it just alpha? Or is it capital share of national income? Okay, and then we're going to set these parameters to numbers. And then we're going to put in the model. So the first thing of some parameters we notice are combination of parameters, right? Like we have this kappa in the New Keynesian-Phillips curve, which was actually this a combination of some parameters, or lambda in the New Keynesian-Phillips curve was this 1 minus theta times 1 minus beta theta divided by, right? It was a combination of parameters. We can define these composite parameters inside the model sector with this hashtag out in front of it. You could also put it up here, define it as a normal parameter and put it up here, but there's sometimes, if later on you're thinking about estimating the model or running a lot of experiments where you change some other parameters, it can be, you can run into the problems if you do it that way. So it's just, inside this model declaration, it's a better way to do that. And the reason why is that whenever you rerun Dynare or Dynare starts changing things, it's always going to recalculate everything that's in the model declaration. Now, we have, when we declare the model, if the model's not linear, we shouldn't call it linear. And even if it is linear, we don't have to call it linear. But doing so helps the computer save some time. When it sees these equations, it's just going to type them all up and throw it at the computer. If we give Dynare a nonlinear model, it's going to start trying to approximate for us. So it's going to start calculating derivatives and fixed points and this and that, which if we've already log linearized the model, if we've already done the derivatives, right, then the computer doesn't need to do that. And what's the big deal? Well, if you're estimating the model, you might need to recalculate the model for different parameter combinations, 1,000, 10,000, 1,000,000, 10 million times. And if the computer is taking derivatives 10 million times of something that's already been linearized, it's wasting a lot of computer effort. And so that's just the way to do that. And now we start typing in the equations. I think we have our nonlinear, or we have our, our New Keynesian-Phillips curve here. Before it, Johannes gives the equation a name. That's very useful. And also tells you what the equation number is in the book. So in a lot of the output from Dynare that we're going to get, you're also going to see what's the name of the equation, where can we find the equations. It's just very good practice, transparent practice, right? It's easy to follow his programs and look at the textbook and see what they are, right? So we have our New Keynesian-Phillips curve. Now, if you look at this, on our New Keynesian-Phillips curve, we have pi t is equal to beta times the expected value, time t expected value of pi t plus 1 plus kappa times the output gap at time t. And if you look at this, what's missing is t. We already up above told Dynare, look, when you see pi, that's a variable. And we also told Dynare up above, I think that was here, pi is in the variable section. I also told Dynair, look, when you see beta, that's a parameter. So when Dynair starts looking at this equation, it sees, aha, I have a variable equals a parameter times a variable plus a parameter times a variable. Now, we could have write t for all of our variables, but since t is the natural starting place for all of these, we decided to save our typing fingers by recognizing that a variable, if you don't say anything else, you've called it a variable, and if you don't say anything else about it, it's going to be assumed it's time t. So because pi is a variable, and there's nothing else there, this means it's pi t, inflation at time t. The forward-looking component of our New Keynesian Phillips curve, you see over here. It's pi parentheses plus 1. So this plus 1 in there is telling it to take t and add 1 to it. Expectations is also not there. It's assumed that everything is the time t expectation of a variable. There are ways around this and some alternatives. There's a 200-page manual to describe it, but the standard way, if you have a future variable, if it's plus t, it's not inflation plus t, but it's the time t expectation of inflation at plus t. So that right there, what's written there, is actually et of pi t plus 1. So a good way to think about it, if we look at this, what happens, what do you think we can need if I were to change this to 1 into a 2? What do you think this is going to mean? This would mean exactly. So this is the time t expectation of pi t plus 2. Oh. Okay. All right, then we have our IS term. Output gap today is equal to the time t expectation of the output gap next period minus 1 over sigma times the deviation of the real interest rate from the natural rate. Here we have I we define up above, that's a variable. Right. That's going to be here our nominal interest rate minus pi plus 1, so the time t expectation of inflation in the next period. And we have some of our natural rate of interest, natural output. We have our technology or TFP shock. We have our monetary policy shock, which is the one we just looked at together in the lecture. There's also, we're not looking at this lecture, there's also a possibility for a preference shock. That's a good thing we should add. Okay. And then for our figures, we don't want to give the quarterly interest rate. That doesn't mean a lot to people. We like to think of things as annualized. So we have the annualized nominal interest rate. It's 4 times this quarterly. Do the same thing for the real interest rate, the net interest rate, inflation, etc. We have then our price level. Well, if we have inflation, what is inflation? It's the log price today minus the log price yesterday. Look here, we have P. The first P just means it's PT, and the second P, we have parentheses, minus 1, so it's PT minus 1. Now we don't have to deal with expectations here because at time t, we know everything that's happening today, and we still remember what happened yesterday. You know, we're not forgetting, so this is just PT minus 1. They added some other variables that we have along the derivations. Right? The real wage we saw in our labor leisure trade-off. marginal product of labor is what's going to, the demand side is going to clear that market. Dynaire also wants us to define the shock variances, right? Some stochastic properties. Now, if we're estimating the model, if we're looking at real data, we want to estimate what the actual standard deviation is of these monetary policy shocks, for example. However, we want to look just at the theoretical impulse, and Dynaire, by default, is always going to give you the impulse response to a one standard deviation shock. So we're going to define the standard deviation, right, as 25 basis points, so it's one annualized percentage point is a standard deviation, not because we think that's the standard deviation of monetary policy shocks, but because this will give us from Dynaire an impulse of one standard deviation, which would now be one annualized percentage point. Dynaire has some checks here. It's going to calculate some residuals. If you have a nonlinear model, calculating the steady state can be difficult. So you're going to give it a guess, all right? And it's going to tell you how close your guess is, or to see if there's a problem. It's going to calculate the residuals of the dynamic model when you insert, or the static model when you insert a steady state into it. If the residuals are small enough, it's going to put them on with a steady state. And then it's going to check some properties. One of the properties it likes to check is going to be the equivalent of this property. That's going to be very important, these eigenvalue properties. And then we can start generating output. So with the IRS, the monetary policy shock, or the discount or preference shock, we don't look at together. And we also have then we also look at the preference shock and the technology shock. Okay, and the way we call Dynaire, when we ask Dynaire to calculate the solver model, is the command stock simul, or stochastic simulation. And Dynaire is going to calculate a number of things, and there's a whole bunch of default parameters. But here, we told Dynaire it's a linear model. Let's make sure we just do a first order approximation. Right? Don't try and take derivatives. And we want our IRFs to go out 15 periods. Right, here we already did 12. We'll change things in a minute, but first we're going to leave things the way Johannes did them. Okay. Now I want to go a little bit smaller, but I want to calculate, have Dynaire go through this program, build the model, write the MATLAB files to calculate and solve the model, including running this stock simple program from Dynaire to calculate the impulse responses. So I just type Dynaire and the name of this mod file, which is Galilei 2015, chapter 3, and I hit, oh no, we don't have the microphone on. That's okay, you all been paying attention. Huh? And Dynaire starts calculating, printing up lots of results. caught up, I'm going to clear one things again. Right, one second. Clear all. Tells Dynare to clear the workspace. I forgot to do close all, close all graphic, and then CLC clears the screen so you don't have. Now we'll just let it run into its thing. Start looking at some of the output. So Dynare, right, it just gives us some background information. We called Dynare. We didn't call the command, we just typed the name of the mod file. We can add parameters when we call Dynare to do certain things. Look at the manual. There's a million things you can do with Dynare. It's just telling us we didn't do anything. It starts to pre-process the model file. It found 25 equations. It starts calculating some parts of the model that meet static models and dynamic models, normalizing things. It's faster if it can, if some of these equations can be broken up into blocks. So it found 7 blocks, 6 of which are recursive, and 1 simultaneous block. So what it's trying to do is saying, well, instead of solving a really, really big matrix, maybe if the matrix is a matrix like we had, if it has certain properties, right, I can break it up into several smaller problems. So this is just a computational thing, but it's telling you what it's doing. Okay, the pre-processing was completed. It took it 1 second to do that. Now, it's going through the equations and telling you with a steady state. This is a linear model, so everything is 0 here, but it would be if there was a deviation, like if the steady state that you calculated is different than what would solve the model, there would be a non-zero number here. And because Johannes Pfeiffer was so kind to give all the equations a name, we don't just have a number here, right, but we can also see, right, what equation it is. Oh, that's the equation, that's the IS equation. Right? Is equation number 2. Right? The steady states are all 0. This is the steady state of the log deviations themselves, which are 0. And now it starts calculating eigenvalues. And the way Dynare solves this problem is a little bit it's a little bit different than the way we solve it, or the way Gaudi solves it, because for more general models, just looking at one matrix isn't enough. You need to look at a couple of different matrices, and so you need to have eigenvalues for forward-looking variables. Right? And it's just that we have 2 forward-looking variables, this forward-looking part, and the way that the problem is defined that they solve would be essentially, instead of working with A, they'd be working with the inverse of A. Right? And so the inverse of A would need to have 2 eigenvalues outside the unit circle, so that our A has these 2 eigenvalues inside the unit circle. It's kind of unfortunate that Jordi-Galli did it that way. I think it's more sensible for this problem. We can see straightforward sort of what we're doing with the solving forward. But when we try to connect the more general problem to the software, we have to keep in mind there's a little bit of difference in the definition. Are we working with the matrix A or with its inverse? All right, it gives us some background information about the model. They had 25 equations, it found 25 variables, that's good, right? If you have more variables than equations, you're not going to be able to solve the model. All right, gives us the covariance of the shocks, and now it gives us policy and transition functions. So what we've calculated out in these method of undetermined coefficients is the response of our variables to this shock nu. And so the specific parameter values we chose, these are those numbers. The theoretical moments don't mean much because these standard deviations were chosen just to give us the 1% response. Correlations, and for whatever reason Dynair is hung up here. Maybe I need to restart MATLAB Online. Here we have the impulse responses, which should be the same pictures that we saw before, right? And indeed, we have the increase in nu to 0.25, which should translate to an annualized response of 1 on the interest rate, but it doesn't go up by that much because we have the endogenous response to the output gap and inflation, both of which have gone down by about 0.3. We have our real interest rate response is larger than the nominal interest rate response because of here our decrease in inflation expectations. Right? Here, instead of the money growth rate, we just have the level. This is what I drew on the board. We have this drop on impact, the negative growth rate, and then we have the increasing back up, right, which is this positive rate. So these numbers aren't exactly the same. Let's see, before we do that, in a second we're going to see if we can fix the model or change the model to match what we did in the lecture, and then we can think about if we want to look at something else. When we look at these shocks, though, there's these variables are auto-correlated, right? We have the output gap goes down, and it only slowly returns. Same for inflation. Same for all of our variables seem to have a pattern of autocorrelation. And if we look, they all have the exact same pattern of autocorrelation. This is interesting. we should know why. When we solve the model directly, we saw that these variables are linear functions of z, the exogenous process. So if z is autocorrelated, xt is also going to be autocorrelated, and it's going to have the exact same autocorrelation as z. It inherits the autocorrelation from the exogenous process, which also means the model, this basic Keynesian model, because it's entirely forward-looking, doesn't have its own what we call internal propagation. If something moves slowly or moves quickly, it's given entirely by our assumptions on exogenous processes, which is why a lot of people said, this is great, right? This is a good start. We've got the liquidity effect, right? We've got ISLM and New Keynes and a Phillips curve together. But in order to match what we see in the data, we're going to need more things, more elements in here to slow the model down, to give it some internal propagation. Okay. So now I want you with me, go through, let's change the parameters in our mod file to match those in the lecture. Right? Now, why do we want to do this? When you're doing research, the first thing you want to do is replicate. Right? Because if you do something new, there are at least two reasons why you could get different results than a previous study. One, you have something new, and what you've done that's new is different. Or you made a mistake. How do you minimize the probability that the reason you got into something new is because you made a mistake? Well, the first thing you try to do is I'm going to try to do exactly what these people did, and if I get exactly their answer, right, then at least I know if I change something starting from there, right, it's due to this one change and not because I made some mistake in implementing their model. So. And it's also good for us because, you know, I'm just the professor up here teaching. I can make mistakes too. You shouldn't believe everything I say. Right? So let's see if this actually works. Right? We have this figure in the lecture that the IRS should be this. So let's see if we can recreate that. So we want sigma equals to 1. We want this phi to also be equal to 1. That's different than what was in the book. So I'm going to put a 1. And then a semicolon afterwards. The semicolons are very important in dynamic. A lot of times if something isn't working, it's because you're missing a semicolon. That's the semicolon tells dynamic to end the line. It's always like the command, like a stop. Then I'm going to start a comment. I'm going to say this parameter 5, and this is then on lecture A and G, that's me. Lecture 05. Okay. 5 pi was 1.5. Phi y was 0.5 divided by 4. That's good. Beta. Beta is 2/3, not 3/4. This is the right. This means that on average, we change our prices once every 3/4. The high rigidity that Gali had is probably maybe the more realistic. It gives us about once every year, right? But first, we're just going to follow this. We're not looking at the money growth rate yet. Row 0A we don't care about for now. We want row U to be 0.5. That's good. Beta 0.99. Beta we did as 4 in the lecture. Alpha 1/3. I don't know why he chose 1/4. Okay, and epsilon 6. And now what I want to do, I want to keep these figures. And before I want to close these other charts we have to look at yet. We'll look at together in a minute. Now, I want to go back to the command window. Do that here. Now, we'll go a little bit different. Let's see. The response to the output gap impact is a little bit larger. Okay, so we're getting closer to. Let's see if this is closer to the lecture. Oh, we got the length is wrong. We need 12 instead of 15. And we also want the money growth. And we'll get rid of some of these variables. So let's do that work. I want to add in those guys. First thing we want IRF 12. The output gap, then I want inflation. Right, then I want moving money growth in a minute. First, we're going to switch to real rate. Annual rate. After. And I don't want weighting to the price level. Alright, so now we're getting closer and closer. We can start, I don't know if we can edit all the properties quickly here. We can start thinking about color, blue, and markers. And now we're getting closer and closer to the pictures in the lecture. Look at this axis. Should go from 0 to -4. And we can figure like changing these properties to make the picture closer and closer, right? But it looks like in terms of the size here now, doing good. I'm sorry? So it shouldn't be, it should be, it's just because of the scale of the axes here that I've changed. We're missing, here's the money level, not the money growth rate. So that's the one last thing that we want to do together now. And then we should have pictures that are pretty much the same. That's also something that's, sometimes it's very difficult to get things exactly the same, right? Replication is also sort of an art. I want to add in money nominal. Wasn't included in the equations, or the money growth rule equals 0. I'm going to add it in here, but I also need to make sure that we have it as a variable. Here, and I am, for a second, just for us, I'm going to calculate this all over again. Saved. Store. gives a quarterly money growth rate, so if we want to make this annualized, like in the picture in the lecture, we need to change that definition. We have, let's add in a variable Johannes Pfeiffer's lead annualized money growth rate. Money growth and equal to 4 times growth. Added a new equation. I need to make sure to tell Dynero up top. When you see these letters, this is a new variable. Add it to the bottom of the list here. Money growth annual. Let's follow his convention. Call it then. Oh, we also already had a process. Let's see. Just want to try that one last. Limits. Y limit, we want the nominal interest rate to go from 0 to 0.8. For inflation, we want to go from minus 0.4. Also for y output gap. Growth is good. Real interest rate, we want to go from 0 to 0.8. And U shock. From 0 to 0.4. So Daenerys starts it, the shock happens at 1, and the figures that I'm making start at 0, so 0 is the point of impact. I have to do a little more work to get that to be the same. That doesn't make sense for time. Hopefully now when you look at it and compare them, now you're a little bit more convinced than just a second ago. Now we've got the same responses. Like a lot of this, when we get the scaling right, we're getting the same impact coefficients and the like. Okay. What I want to do now is to think of changing monetary policy, and then we're going to go for lunch. But let's look at a very, very hawkish monetary policy. So let's say increase this by a factor of 4. See if I can do this. Let's do. Now we have the same monetary policy shock, the same 25 basis point surprise, and we see that the response is much more subdued. Why? So this increase, a surprise increase in the nominal interest rate starts to push inflation down. It's a contractionary monetary policy response. And the central bank then starts to respond That's the rate, right? That's the rate. Yeah, vigorously, increasing the nominal interest rate, preventing then a much further rise in a much further decrease, effect of inflation or the output gap. What we can see then here, the response on impact is about half of the nominal interest rate, is about half as what it was before, right? Even though inflation is only a third of what it was before, right? So this difference is there's a much stronger response, right, to a smaller deviation, and the smaller deviation in inflation is caused by this vigorous response of monetary policy. Right, we can think of one last experiment. Very quick. What do you think would happen if we respond, instead of 3 times larger, what if we respond with a response to inflation of 100,000? Right, so monetary policy is obsessed with the smallest deviation in inflation. We have essentially, monetary policy is trying to keep inflation constant, like at any cost. What's then going to happen? This is my figure 3. Monetary policy is able to completely stabilize this shock. Wait a second, we have the same, these look like the same figures. Look at the axes now, it's times 10 to the minus 5. Right, so essentially no variable deviates, because as we have this shock, monetary policy reacts to inflation in these small deviations so strongly that it cancels any effect out on inflation. If there's no response to inflation, think of the new Keynesian-Phillips curve. We have pi t equals beta et pi t plus 1 plus kappa y tilde t. If we manage to stabilize inflation, keep inflation constant, what does that mean for the output gap? It's also constant. So if inflation is 0, then the output gap is 0, right? So that's what's going on here. Monetary policy eliminates the effect of the shock by completely stabilizing inflation. And we will look at more shocks, monetary policy rule, after lunch. And then we can look then at the problem set, and then we'll be done with the new Keynesian-Phillips curve. And we'll come back then to this MATLAB then maybe later today if we have some time, or then tomorrow on Thursday. So see you in about an hour, okay?